My name is Dean Monty, and this video is going to cover some insights that I ran across in doing matching networks, but it turns out that that can be extended to filters in general. And what I'm going to be showing is a way to set filters up in circuit simulators so that you can just tune the filters to different characteristics. And basically each pole of the filter or each resonance of the filter can be independently or in pairs tuned. So to demonstrate where we're going to kind of get to eventually is this circuit I've got set up so you can tune in the bandwidth to any desired bandwidth. You can, and of course you can scale it to any frequency that you want just by multiplying all of the components. And then more uniquely, you can adjust the filter shape. And so we're going to get into the details of how this works. Essentially, it's pairing components at opposite ends of the network, the filter network, and that allows you to control a lot more than normal. In that you're forced to use a uniform distribution, such as if we reset this back to the beginning, uniform distribution of the resonances. But in some cases, you might want to force that to a different combination than what the typical filter equations develop for the different styles of filters give you for a result. So this allows a lot more tuning in this methodology. So that's to give you a visual example. I'm going to go through a bunch of slides and talk about how to get to this point. And I have several other videos on matching networks that go through a lot more of the basics on the topics here. And they cover both the SimSmith free matching network tool and the QucsStudio tool, which is a circuit simulator. And they have lots of details on those. I'll be using those two tools in the examples here on talking about filters. Now the key points that I want to go over in this video are that filters to a large extent can be treated as a 50 ohm to 50 ohm matching network. And so a lot of the principles that I worked with in the matching networks then carried over to talking about filters. And what I found out was that for some symmetric filters, keeping the C equal to the L over the Z in times Z out creates a resonance where L is paired with the C at the opposite end of the network. So normally you might think of stepping through a filter network and the first two components are creating a resonance, but it turns out that it's the ones at the opposite ends of the circuit that create the resonance. So if you keep this ratio and then you scale the L's and keep this C equal L over Z in times Z out, that allows you to move each resonance almost independently. They do have some interaction, but they're pretty easy to just tune in with the circuit simulator. And the fact that we can do this is because we can now calculate 1 billion times a second compared to what was done in the early days of filter development. So it's easy to see what's going on as far as the interactions of the components. At least some asymmetric filters, like the Cower and some of the other ones, even those can be looked at as the components on one end of the network working in tandem with components on the opposite end of the network to create a resonance. So you can still figure out ways to scale those, and I'll show some examples of that. And then standard filters are based on equal ripple, and so this is what we're kind of getting away from, is that all of those equations that were developed in the early days of filtering, we're assuming that you wanted equal ripple, but in a lot of cases that isn't necessarily what you need for the application, that it's better to cluster resonances together to get a particular response. So here we show just a standard Chebyshev filter, and then QucsStudio, you can just plug in some values of what you want for ripple and the frequency, cutoff frequency that you want. And you'll get something like this that's showing the equal ripple in this case, and then the more ripple you're willing to tolerate, the sharper the cutoff you can get. And in most cases, people don't tend to look at the Smith chart, filters on the Smith chart, but they're pretty useful in my mind. And I'm just showing here that what you end up getting is loops of almost like a flower petal pattern on the Smith chart. And if we look at a passband filter, you get even more of that kind of a look, where we've got a series of rings around the center point of the 50 ohm point in the middle. So you get these loops that correspond to the curvature up in here on each one of these creates a pedal on the Smith chart. And so this is a standard Chebyshev passband. Now if we go to a Butterworth filter, it has beautiful symmetry in that what comes through is that if you take the first L and the last C and divide those, you get 2500. If you take the last L and the first C, you get 2500, and so on, working your way into the middle. And so this is 50 ohms times 50 ohms is equal to 2500, so that's where these numbers are coming from. And you can kind of see that in the tables for calculating a filter network, in that what we've got is that you normally take these on this is a table of normalized values for a 1 ohm and 1 radian per second normalized filter, and then you have these equations for denormalizing it back out to a particular frequency and impedance. Well, if you take this normalized equation for L and this normalized equation for C and you divide those two, all you're left with is the impedances squared. So this is 50 times 50 or 2500 in the case of a 50 ohm system. And you can also kind of see that in that if I take this L and this C, and those have the same value down here, and so if you're just working your way across, you really only need the first half of the table if you treat this as LC pairs, flipping them each time. So the L and a C or a C and an L, and then you flip it around, mirror it for the second components, and work your way across. So if we look at that in a schematic, you can draw that out this way, which shows you that you have your input port, and then you have a L at the beginning of the circuit, a C at the end of the circuit, and then you mirror that and create an L and a C for the second resonance. You mirror that again, you get an L and a C for the third resonance and an L and a C for the fourth resonance. So each one of those corresponds to a different resonance over here on the rectangular plot. So the first one, the outermost components, are really fixing the DC resonance, and the second one is setting the next higher level frequency resonance, and so on out here to the highest frequency resonance. And you can see on here that these have unequal ripple in this case, and so we get a big ripple out here at the highest frequency case. That's the outermost ring on here. And so you're starting off with DC in the very middle at 50 ohm point, looping around for the first resonance, second resonance, the third resonance, working your way to the outside of the Smith chart. However, I can now set up tuning elements for all of these, and basically by adjusting the inductor values in each of these and letting the C's track those at 2500 to 1, and that being able to adjust these resonances to cluster them together by adjusting these multiplier parameters, and that basically forces all those into closer and closer, shrinking those rings into the 50 ohm point in the middle of the chart. Now you can also add shunt inductor, an extra inductor on each one of the capacitors, and create these resonances out here that will then block higher frequency signals. So we've adjusted the L and the C to keep all of those in the 2500 to 1 ratio up here, except for the C we've added in an inductor. That then means you have to reduce the amount of capacitance to account for this inductor that's in here, so you make those a tunable parameter. And now I can end up just using adjustments of tuning variables to then move all of both resonances in band and resonances out of band around. And an alternative way to draw that some people might find more intuitive is just this horizontal approach, where you end up saying that I've got a unit cell where I've got an L and a C, those are at opposite ends of the network, and then a C and an L inside of that, and then that can just be copied multiple times for however many resonances you want, and you can do a half unit cell as well. So just delete the last section and short it out if you want to do a fewer than a multiple of 2 sections. So what that lets you do then is just squeeze all those resonances together, and in a lot of cases, rather than having a low pass filter with a lot of ripple up here near some particular frequency you're working at, you may want to have better performance right around that frequency, and then still an improved cutoff frequency performance. Now, I find it useful to also look at the symmetries of these filters in the SimSmith tool, which is normally a matching network tool that you're using for doing significantly different impedances, but it's useful to draw the filters on the same kind of a system so that you can see the symmetries. So here what we've got is 3 different frequencies where all of that component translations, and again, these are at 1 frequency. So this is talking about 3 separate frequencies and the translation the components make for the impedances and admittances on those charts as you step through the filter. So this first section shows closest to DC. If we actually took it all the way to DC, these would all collapse down into a single point in the middle at 50 ohms. So then this is the first resonance, second resonance, and third resonance. At all of the frequencies, this becomes asymmetric, where and you can see that better here, where this is back to the example where I have 2.5 nanohenries for all of the inductors and then 1 picofarad for all of the capacitors. So you get 4 distinct resonances out here. And at the, again, at the very DC, this would all collapse down to a single point in the middle of the chart. At this first resonance, you get this interesting pattern here. And then if we look at the other two resonances, we get these patterns. So this is the same thing I showed on the last slide for that first resonance. And again, DC down here, it'll all be collapsed into 1 point in the middle of the chart. This one then shows the next resonance, showing that it's a symmetric pattern about the vertical axes. And then at the highest frequency resonance, we also get a symmetric pattern about the vertical axes, always looping back to the 50 ohm point. So it goes through a series of steps for each of the LC components and it works its way back to the 50 ohm point. Now, a Chebyshev filter is a little different. It's not a symmetric filter, and in fact, it kind of shifts off to the side to along the real axes to different impedance points. So if you go through and calculate the first inductor divided by the last capacitor in a Chebyshev filter, you don't get a constant 2500. However, you can add in tuning elements where you still say, well, the first components are combined with the last components can be scaled, and then that moves resonances around. I can do that for any combination here where I look at these components matched with that C, this component matched with this C for the highest frequency is the center section. And so all of these can be tunable to be able to tune both the main frequency that you care about. So we say we don't care about these lower frequencies, but we do care about the band that we're working in. And then we also care about trying to block high frequency signals. So in this case, with a Cowher filter, instead of using inductors in the shunt leg of the caps, we now have these inductor capacitor pairs that create these resonances out here for blocking high frequency. But again, you can just set up multiplying values that scale combinations of these elements to create what you want for performance. And this one is a tunable Bessel filter. So basically I start off with a Bessel filter that's a standard one that you can go up to the tools section within this QucsStudio tool, create a filter, set what type of filter you want, whether it's passband, low pass, and what type it is, and then some parameters, and create those filters. But we can then go in and create multipliers for combinations of the filters, the LC combinations from the outside elements, the next elements in and next elements in, and so on, and be able to control the tuning of these. So here we can see that we've got went from a fairly slow roll off of the filter performance to a fairly fast roll off of the filter performance. Are affecting this intersection as well. We're getting better performance out to a higher frequency. That may be at a trade-off for the not getting as good a performance like phase issues. And here is another modified Bessel filter, but here we've added in the inductors in the shunt legs of the caps, or for any cap that's connected to ground, we're adding in a inductor in that leg. And that's creating these 3 outside harmonic traps, or high frequency blockage resonances. Okay, now this is showing that you can just go directly to the SimSmith tool and create filters by just looping around the 50 ohm point and back to the 50 ohm point. So this is a simple L, C, L, and C to get back to 50 ohms. So that creates a Butterworth style kind of filter that ends up being a low pass filter. And then on top of that, I can take the capacitors that I put into here and note the values of the caps, then replace them with an LC with this L in the shunt leg to then add in a couple of resonance higher frequency traps down here. Now this is just an example of taking basically doing an L to get up to here, a C to get down to this location, and looping around multiple times, then coming back up to 50 ohms again. And so you can get this kind of a response where you've got a nice, really steep roll off. You've got a good performance within a band very close to the cutoff frequency. So this is essentially a higher performance filter than what you would get with a lot of other topologies. This is just another variation of it where I've squeezed 3 of the resonance close to the cutoff frequency, and you get a nice steep roll off on that as well. And so this one is done in QucsStudio versus the last one was done in SimSmith. So in this sample, I've just pushed the resonances closer together and more of the resonances towards this passband region that I care about. And then that results in a nice steep roll off out here. In this part of the video, I'm demonstrating a Cower filter that was created using the tools within QucsStudio. And that's Cower filters done with these third order and with this frequency. And so what that does was create a prototype that I can then go in and add multiplier values that just scale everything. So if you want to move the whole response within frequency, just multiply all the components by a variable. But then when you want to try and move the spread of the resonances or other parameters, you rearrange multipliers for the other components that are in balance. So I end up having inductors on one end of a circuit or balanced with capacitors at another end of a circuit and vice versa. And so you can go through and figure out what is being multiplied by what in here. In some cases, it'll be an inductor multiplied by a value, and then the capacitor that goes with it multiplied by the reciprocal of that value. But what it does is give me variables that I can adjust the target frequency up and down. And then you have the spread of the resonances. You know, spread those out, which is trading off the performance within the band with the depth of the trenches. And then you can also, in this case, be able to move the out-of-band response by a couple of different parameters here. Those are affecting those shunt inductor cap combinations. And so it just gives you a lot more versatility than what you have in the typical using the built-in tools for filters, so you can visually adjust things. Now there's some other insights in here that you can treat these. So before I showed just a simple where I did an L and then a C, an L and a C, but you can break that up into an L and a C that go from one impedance to another impedance and treat that as one element, and then a C going down from this higher impedance down to a middle intermediate impedance and back up to a low impedance as another LC pair, and then going up through an LC final pair to get to the 50 ohm point. So in this case, what that creates is this resonance at DC and then at some higher frequency. And you can go further. So this is an example where I've taken that concept and gone through this combination of an LC down here, and then another third LC up here. Put that into a network like this, and then use the calculations for these. These were mostly gone over in the other videos on the matching networks, but you basically are taking the impedances, the input and output impedances of each section, and figuring out what the LC is that matches those. And so in this case, I've got two capacitors here. Those later would be lumped into one capacitor, but we've broken them up for the purposes of doing these calculations into two. The same goes for these inductors. These will be combined later, but for right now they're being treated as two. So I get this LC pair, that LC pair, and the final LC pair, and run through these calculations using the impedances to get the LC pairs at each jump in this trace. Now, one thing that's unique here is that the Chebyshev filter showed us that you didn't need to have a symmetry about the vertical axes. So this example is showing that I can do an interesting pattern here where I go down with a capacitor, up along this line, back over here with a shunt inductor, through here with a series cap, back up, and then go up through a final L and C to get back to 50 ohms. That gives me 3 resonances and a passband type topology. And you can see that there's 2 small loops in here very close to 50 ohms. So that's creating these 3 points here across the 50 ohm point 3 times due to these 2 loops. So this is a non-standard topology I don't think you'd see anywhere else. And then on top of creating that, and this is nice because it's only 3 capacitors, and then the rest of these inductors could all be done as microstrip transmission lines on a PC board. So here I've added in inductors into the shunt legs of those 2 capacitors that were shunt capacitors in that topology. And so now we get decent high frequency traps out here. So that's showing that once you understand these symmetries, you can extend it to doing unusual things that you wouldn't normally be able to do with the filter equations. This example is based on starting out with a prototype filter that is just based on making all the inductors all 2.5 nanohenries and all the capacitors 1 picofarad, so that you have a balance of 2500 to 1 for the cap to the inductor values. And then adding in a bunch of equations to calculate different variables. We have a CF for center frequency to adjust the whole response up and down, and then various other parameters to scale opposing, basically looking at it as a high pass and low pass combined. So the inductors in the first leg are matched up with capacitors in the shunt leg, and vice versa. And so that's from one end of the circuit to the other is a pair, and it's both paired with the inductors paired with a capacitor, and the capacitor paired with an inductor. That then gives us these variables that we can play with. So you get CF for center frequency, and so I can just move the whole response up and down, and then move the bandwidth up and down for wider bandwidth and narrower bandwidth, and then balancing in this case 5 different resonances. You can change the outer ones versus the inner ones. Get different shapes of responses that might be useful for certain applications. Basically, when you cram all the resonances together, you're getting something more along the lines of a Butterworth filter. And then you can see major changes if we especially watching the Smith chart down here. As I change this last parameter, you can see that you get loops on one side of the Smith chart and swapping over the other side of the Smith chart, and getting extremely steep cutoff frequencies, but also more losses in band. And for this particular model, then you can just hit reset and get back to starting point. So that's kind of an optimal setup for this controllable passband filter. And the end values are then shown up at the top up here, so that you can go off and use those in an actual circuit in a more complex circuit. The important takeaways to this talk are that resonators are made from LC pairs at opposite ends of the filter, and as you add more pairs of LC pairs, you mirror those as you insert them in the middle of that circuit to create a new resonance. Then by scaling the L's, while you keep the C values equal to the L divided by Z and times Z out, allows moving each resonance almost independently. And that's true for these symmetric filters. It gets more complicated as you get into the asymmetric filters. Having unequal ripple may benefit some applications where you don't really want equal ripple because you want a particular band to have the best performance. So you move those resonances to where it'll do you the most good. And finally, the new filter topologies are possible when you understand the relationships and symmetries of the resonators. That concludes this talk. Thank you for watching, and if you think you find this information useful, please like and or comment on the video. And if you haven't watched the other videos and would like more information about how to actually use the QucsStudio and SimSmith, please check out my other videos.